Welcome back everyone to part 2 of the VXLAN multi-site fabric setup. In this video we're going to start looking at the layer 3 side of the fabric and creating a tenant VRF and a layer 3 VNI. And then as a second part of that we're going to split them out into two different tenants. So first thing we'll do is we'll put VLAN 1000 and 1001 into the same tenant so they can talk between themselves. And then we'll split that out so we have VLAN 1000 and 1001 in two separate VRFs so that they can't talk to each other, and that would sort of signify maybe two different companies or two different environments sharing the same fabric but us not wanting to, well, essentially kind of trying to keep them separate and not allow connectivity between. And then we'll finish this video off by configuring route leaking on the border leaves, so DC1 leaf 2 and DC2 leaf 1, to essentially re-allow that communication but keeping the VRF still separate. So in the last video we set up all of the layer 2 side of things, so we should, and we'll just test, make sure that we still have layer 2 connectivity. It looks like we do. Let's just test something to the other data center. Perfect. So it looks like we've still got layer 2 connectivity as we'd expect. So first things first, the same as any standard VXLAN fabric that we would want to enable layer 3 on, we need to create some Anycast gateways. So they're leaf only. So what we need to do is we need to do fabric forwarding Anycast gateway MAC, and then we'll do A, B and C, and then this is essentially for all of the leaves. You do want this MAC address to be the same for all of the leaves, because if you think about, you know, something like VMware or Hyper-V, where you can move VMs across essentially different servers and say they were on different leaves, you would want that VM when it moved to not have to re-ARP for its gateway. So if you have the same MAC address across all of the leaves, then essentially it prevents that from needing to happen. So we'll get this on the leaves in DC2, like so. And then we need to essentially the SVIs we're going to create for the Anycast gateways need to be in a tenant VRF. So we're going to create that VRF first. So VRF context tenant 1. We'll set the VNI to 900.101, and this is essentially like the VN segment that we set on the VLAN ID. This is a similar, it's a network identifier for this VRF. So we'll set the RD to auto, and then under the address family IPv4 unicast we will set the route target for both, so both being import and export, to auto, and the same for EVPN. Essentially what this auto is going to do is it's going to take the autonomous system number and this VNI, and that will make up, so in the case of DC1 the autonomous system number is 100, so we would expect that the route targets for these the routes that are within this VRF will be 100:900.101, and then likewise in DC2 we would expect that to be 200:900.101, and that's what we should see a bit later on when we look at the routes. So this VRF tenant 1, for some reason it gives me the VNI last, and when we apply this to another leaf it'll complain because it can't generate a route target without the VNI being configured. So I'm not sure why it gives us it in that format, but we'll get that on the other leaves as well. Copying the wrong thing. What I'll do just to be safe is I'll swap those around. Perfect. So now let's create the SVIs. So VLAN 1000 and VLAN 1001 at the minute they're going to be in the same tenant because we want that intercommunication. So in VLAN 1000 I'm going to no shut it. We'll say VRF member tenant 1. We'll do that first, because if we then if we put an IP address on there, it's going to strip that off as soon as we apply a VRF. So this is the address we're going to use. This address has also already been configured on the PC or the virtual PCs as the gateway, so we don't need to do anything there. And then last but not least, we need to say that this is a fabric forwarding Anycast gateway, fabric forwarding mode Anycast gateway. There we go. And then we'll do the same for VLAN 1001. We'll say no shut. We'll put it into the VRF. And then the IP address here will be 10.20.1.254. And same fabric forwarding mode Anycast gateway. So we should be able to ping these SVIs now. So let's just let's try from here. You can see there we go. We can ping that from PC1 in DC1. So let's essentially put this configuration on all of the other leaves. So show run interface, see if we can get them both. There we go. And the same in DC2. Perfect. We'll just test one in DC2 to make sure. So ping 10.20.1.254. In fact, there we go. Ooh. Perfect. Cool. So what we need to do now is we need to start layering the L3VNI stuff on top of that, because we need more than just the gateway to be able to actually get that traffic off the leaf and elsewhere. So let's start by adding a new VLAN. So VLAN 999. We'll set the VN segment to 900.101. So that's the same VNI as we set in the VRF here. So VLAN 999 is essentially the identifier for the L3VNI. So we do need to do this on the core switch, or some of this on the core switches as well, which we'll do afterwards, but for the minute we're just focusing on the leaf configuration. So this L3VNI needs an SVI, so interface VLAN 999. We'll shut that. We'll say VRF member is tenant 1, and we don't need an IP address, we just need the word IP forward. And then last but not least, in the NVE1 interface, we need to say member VNI, and then the VNI ID, and then associate VRF. Essentially that's what associates this VNI as being an L3VNI with this associate VRF command here. So let's create VLAN 999 on the other leaves. So DC1 leaf 2, DC2 leaf 2, well, the DC2 leaves essentially. Cool, and then interface VLAN 999, we'll apply the interface as well, the SVI. And then last but not least, we'll jump into the NVE1 interface and apply that last bit of configuration, which is just this associate VRF command here. So if we try and do a little bit of testing now, what we should see is that we should be able to communicate within the local data center, but we shouldn't be able to reach outside of that data center because we haven't configured anything on the cores yet. So as an example, VLAN 1000 PC1 has this address. We should be able to ping the local VLAN 1001 version of this PC, so 10.20.1.10, and we can. So that's good. That's a good sign. It means at least at the local leaf, we're able to get between the two VNIs. And if we try .11, there we go. That's working as well. So essentially, we have tested local DC routing. If I tried to go to .13, I would expect this to not work because it's going to hit the core switches, and the core switches aren't going to be able to process that traffic. So at the minute, we expect that not to work. So what we need to do to remedy that is to do some configuration on the core switches. So first off, we need to create the VRF. So let's grab this VRF config, flip these around again, do that on all the cores. Perfect. Now we need to create VLAN 999 and set the VN segment to 900.101. Do that on all the core switches. And then we have to do the same, so we create an SVI for it. So interface VLAN 999, and the exact same configuration applies, so no shutdown, VRF member tenant 1 and IP forward. And we'll apply that to the other core switches. Just like so. And then again, last but not least, under the interface of NVE1, we need to say member VNI, the VNI ID, and then associate VRF. Do that in DC2. Just like that. And in theory now, this ping that didn't work, as long as that PC has populated its local ARP expression cache, we should, as we can see now, be able to communicate with it, which is perfect. So we've now got inter-DC, inter-VNI traffic fully functional. So we can communicate with devices from DC1 to DC2 and between VLAN 1000 and VLAN 1001, and we'll just verify that from a DC2 perspective. So for example, this PC here, which has got 10.20.1.12, we should be able to ping the 10 counterpart of it. If I put the word ping in there, which we can, which is a good sign. And then let's try something in the other data center, so .10, and again we can see that that's working. If we do a trace route for both of those, we'll be able to see the path that it's taking. So let's just do a trace. We'll see, yeah, that because this is on the local local leaf, we only see one entry. If I did, for example, 13, we now see 2. So this is the local leaf. This is the remote leaf, and you can tell that by looking at the latency. Normally, it's a step above what we would consider local, being kind of a millisecond. And then then this is the end host. If we did something across the DCI, we'll see that this is the local leaf. Then we've got the DCI infrastructure up here, which is oddly shown as all zeros, and then this is that remote leaf, and then we get to the final destination. So we can prove that's all working, which is good, but currently we are single tenant, so all of these PCs and VLANs are considered the same logical construct essentially. They're all in the same tenant VRF. So what we'll do now is split that out. So we'll have VLAN 1000 and VLAN 1001 essentially in separate VRF instances. So we'll start on the leaves and we will create a new L3VNI. So VLAN 998, set the VN segment to 900.102. We shall do the same on the other. In fact, this configuration is going to have to go on the cores as well, so we may as well do it on all the cores and all the leaves at the same time. So VLAN 998 everywhere. And then into DC2. And the DC2 leaves. Perfect. So we do need to create a new VRF as well. So if we do VRF context, and we'll just call this tenant 2. We'll set the VNI to the same as we set up here. We'll set the route distinguisher to auto. Then the same under the address family of IPv4 unicast. We'll set the route target for both to auto and for EVPN. And just to show what I was talking about before, if we while we're on this core, if we have a look at show BGP VRF tenant 1 L2VPN EVPN, and we look at 10.10.1.13, this is we can see by this identifier here that this is a route that's come from the other data center. We can see it's a type 2 route. We've got a MAC address and an IP address /32, and we can see here that this is where the route targets come in. So this is the one that was applied for the L3 VNI. So we can see 100, 900, 101. That's the route target of the VRF. And then this route target here is the L2 VNI that it's part of, being 200, 1000. So we can see that that's where that auto route target comes in, and that's how it's built essentially. So it's just good to see that. But let's finish off this second VRF configuration. So let's VRF tenant 2. Again, it's done that weird format, but we'll paste this onto the other cores and the other leaves. And the same in DC2 on the cores. Just make sure it's taken that command. Cool, so we've got VRF now on all of those switches. So we do need to create an SVI for VLAN 998 as well. So interface VLAN 998, no shuts, VRF member is tenant 2, and then we'll just do IP forward. And again, you'll notice there's a lot of repetition with this configuration in terms of it going on a lot of devices, and it's just the same configuration, so a lot of copying and pasting. But we'll get that where it needs to be. So again, all the cores and all the leaves. And then last configuration for the L3VNI is that we need to add it to the NVE interface. So interface NVE1, member VNI 900.102, and then we will associate the VRF. So if we did a show run interface NVE1, we can see that two L3 VNIs can coexist. So essentially we now have two L3 VNIs in here, which is, totally fine. Let's get that everywhere else as well. So got a complete configuration. finally the DC2 leaves. Perfect. So that is the L3VNI setup. What we need to do now is we need to essentially move the VLAN, the SVI, sorry, for VLAN 1001 to the new VRF. So at the minute, if we do a show run interface VLAN 1001, we can see that it's currently a member of the VRF for Tenant 1. So all of the configuration that we've just done now is just creating that L3VNI. We haven't actually moved anything off, so we should still have all of this communication as we'd expect without any hiccups. So what we need to do is essentially reconfigure this SVI on all the leaves and change the VRF member to be Tenant 2, bearing in mind that it will strip off this configuration when we change the VRF member. So we'll say VRF member Tenant 2, and then yeah, we'll need to add this configuration back on because it will take it off when we change the VRF. So show run 1001, we'll grab this configuration. This is only for the leaves, so we'll just paste this on all of the leaf switches. And what that will now have essentially done is it will have separated those two VLANs. So this communication that did just work should no longer work, and we'd expect that. And the reason for that is that we've now separated the routes. So if we were to look at the VRF routing table on DC1 Leaf 1 and do a show IP routes for VRF Tenant 1, we no longer see any 10.20 routes in here at all. We just see 10.10, and then if we looked at Tenant 2, we only see 10.20. So whereas before, when we didn't have the SVIs in different VRFs, we would see all of these routes in the one Tenant 1 table, but now they're essentially separate and there's no leaking of routes. So essentially it's not that we've told the two VLANs that they can't talk to each other, you know, via like an access list or something. It's literally just that the routes don't exist and there's no way to get the traffic between them. So essentially what we want to look at now is, say these two VLANs were, you know, separate companies or they were separate environments, but you wanted some level of communication between them. You know, say it was two companies that were merging, or it was, you know, a common services VRF, for example, and you wanted the tenant VRFs to be able to consume the common service. This is essentially what you would do with the route leaking side of things. So let's come back onto the leaves. So essentially we have we've got DC1 leaf 2 and DC2 leaf 1, which we've elected as border leaves. So they will be the ones that do the VRF leaking. We won't do any VRF leaking on DC1 leaf 1 and DC2 leaf 2. They will essentially just have routes that point to the border gateway, and then the border leaf, and then they will essentially do the routing for us. So DC1 leaf 2, let's start by, essentially you can do this in a few different ways. So you can either advertise the subnets themselves using BGP and essentially kind of attract the routing to the border gateway. So you can either advertise the individual routes, you could advertise them as a BGP summary, so an aggregate, or you could use a default route essentially that kind of attracts the traffic to the border gateway. Because of what we're going to be doing with the firewalls in a later video, we're not going to use default routes, because the idea of that is that we will advertise a default route from the firewall. So what we're going to do in this scenario is we're going to advertise a summary address. So 10.10/16 and 10.20/16 we will essentially advertise from the border leaf to say, you know, come to me if you need to get to these subnets. So we can do that using BGP, nice and easy. So let's just look at the BGP configuration we've got at the minute. we'll see that there's nothing relating to any VRFs in here. So what we want to do is router BGP 100, say VRF tenant 1 will come into the address family IPv4 unicast, and we will say aggregate address. So in tenant 1 we want to advertise 10.20.0.0/16, and we want to say summary only. So that's going to say if you're in tenant 1 and you want to get to tenant 2, essentially come to me. And we'll do the same thing for tenant 2, but we'll change the route to 10.10, just like that. So we should see, if we do a show BGP VRF tenant 1 IPv unicast, we'll see that that is there. And let's just have a look on the other leaf. We'll see that we don't see that yet, and the reason that we don't see that yet is because there's no routes inside of the summary to trigger it to be advertised. Until we do the route leaking, we won't see any 10.20 routes in here, and that's, you know, what BGP will use to be able to advertise that. It can't just advertise it when there's nothing actually in the subnet to summarize, essentially. So let's do the same thing in DC2. So DC2 leaf 1. Let's just again check the BGP configuration. You see we've got no VRF configuration in there, so router BGP 200 tenant 1 address family of IPv4 unicast, and we'll say 10 not additional pass aggregate address 10.20.0.0/16, and we'll say summary only, so that we only advertise the summary, because really we don't need to be advertising all of the individual /32 routes to all of the other leaves. The point of the border leaves is that they do the heavy routing of the lifting and that side of things, and then the other leaves just kind of get the traffic to it. So we don't need all those specific routes because they're all essentially going to point to the same place. Do the same for tenant 2, and we'll just change that to 10.10. And we'll do the same. We'll do a show BGP VRF tenant 1 IPv4 unicast. We can see that our summary's there, but it's not yet being advertised, and we should see the same thing for tenant 2. Same thing, it's there. So essentially now we need to actually configure the route leaking. So we'll do that in DC1 first. So let's just have a look at the VRF configuration that we've got at the minute. So we can see tenant 1 and tenant 2. So let's do tenant 1 first. So VRF context tenant 1 address family IPv4 unicast. So we will say route target import, and we'll say 100 colon, and then we'll use the VNI of tenant 2. So this is where this route target auto comes in. This is what it generates. And I said this before, it generates the autonomous system number colon the VNI. And essentially we want to import routes that have that route target. And then we also want to add the EVPN keyword on the end of there as well. And then likewise for tenant 2, we want to do the same thing, but we want to say 101, because then this is us pulling in the tenant 1 routes. So we'll do the same thing and we'll say EVPN. So if we do that command again now, we'll see that we've still got the auto commands, but then we're also importing a specific route target in each. And what we should see is, whereas before when we did this command, this wasn't being advertised, you know, it didn't have any best or valid markers here. If we do this now, we should see that we've got more routes than we do. So in here we can see that we've now got specific 10.20, albeit they've been suppressed because we've got the summary only, and we can now see that we've got identifiers here to make this an essentially valid route. So if we do the same thing for tenant 2, we'll see that that works the same there as well. So that all looks good. Let's jump onto DC2 leaf 1 and do the same thing for the VRFs. So show run section VRF just to see what we've got at the minute. You can see tenant 1, tenant 2, VRF context, tenant 1, address family of IPv4 unicast, and we will say root target import, and then this side it's 200 colon, we'll say tenant 2 EVPN, and then under tenant 2 we'll do the same thing, but we'll just flick this to 101 and then EVPN. And the reason we're specifying 200 in this data center is because that's what the local autonomous system number is. So again, whereas before we saw a similar thing with the BGP table, if we look again now, we should see that we've got more routes in there, which is what we expect, which is good. So if we look at the other leaf, so a non-border leaf essentially, and do that again, we'll see that we do now see this summary address that we didn't before. We'll see for tenant 2 as well, we see a 1010. So for kind of simplicity's sake, tenant 1 is 1010, tenant 2 is 10.20, and we can now see the kind of inverse being advertised via the border leaf, which is in DC1's perspective 10.0.1.10. So what we should be able to do now is do a little bit of testing, and there's a caveat that I want to show you as well, which is only relevant for devices that are connected to the border leaf. So initially, let's go from this PC here to this PC over here. So PC1 in VLAN 1000 to PC4 in VLAN 1001. So this is that address, and let's try pinging that address, and we can see that works as expected, because we've now got that VRF leaking. If we trace that, we'll see that we see a little bit more in terms of hops. So this is our local leaf, this is our remote leaf, but within the same data center. And then we jump over the DCI, and then we hit the remote leaf, and then the remote endpoint. So let's then test that to a device that's on a border leaf. So for example here, DC1 leaf 2, let's try connect to VLAN 1001 PC2, which is this. And we'll see that that doesn't work, and there's a very good reason why it doesn't, but it's just something that we need to kind of be aware of when we do this configuration. So if we have a look on DC1 leaf 1, if we do a well, essentially, I mean, we've got the route table here, so that the PC we tried from is in tenant 1. It has a route for 10.20.0.0/16, and it's going to send it to the border gateway, or sorry, the border leaf, which is DC1 leaf 2. And then if we look in here, so this is still the tenant 1 route table, we can see that there is an entry, or in fact we can see that there is not in here an entry for the address that we were trying to communicate with. So 10.20.1.11 is not there essentially. If we just have a look at the route table, so show IP route 10, what was the address, just so I get it right? Like so, VRF tenant 1, we can see that it's actually sending it via the null 0 route, which is obviously not ideal. So that is just going to bin the traffic as soon as it hits the leaf, which we obviously don't want. And the reason why that's happening is we haven't pulled that route into the BGP table. So if we look at our show run section BGP, we can see that we've got these aggregate addresses in here, but we also need to advertise the actual subnets specifically that belong to the tenant VRF. So, for example, tenant 1, we would advertise 10.10, and VRF tenant 2, we would advertise 10.20. So if we do that, we'll be able to see the results change. So if we come into VRF tenant 1, address family for IPv4 unicast, and we'll say network 10.10.1.0/24, and then if we come into tenant 2 and do the same thing but for 10.20, and we come out and we have a look at this, we'll now see that we see that specific route in there, and we see that it's attached exported and it's via tenant 2. So we now get that in the tenant 1 VRF table, which is where that traffic's coming from. So if we, where this ping didn't work before, if we try it now, it works flawlessly. So we just need to bear in mind that when we have devices that are connected to the border leaf, we need to make sure that we advertise those subnets into BGP. Otherwise, we'll essentially black hole traffic local to that border leaf. So we need to do the same thing in DC2. So if we jump onto DC2 leaf 1 and do something similar, so something connected directly to DC2 leaf 1, for example, VLAN 1000 PC3, which is this, that's its address. So if we do a show IP routes VRF tenant 1, we'll see that obviously we have a local route for that. If we do it via tenant 2, we'll see again that in fact this is because I've advertised them in DC1. You see that the tag there's 100, which means it's been advertised from DC1. But if I come onto here and come into VRF tenant 2, and just remove that network command, address family IPv4 unicast, no network, and do that same thing. In fact, wrong one. I need to do tenant 1 like so. We'll see that that switches back to where we expect it, to the /16 and the 0, which is essentially going to black hole the route. So we do definitely need it in both data centers. We can't just get away with having it in one. So we'll reinstate these. Essentially, what's happening is it's putting that network into the BGP table, which then leaks it across the two VRFs. Because an interesting caveat with the route leaking commands with the route target import is it will only take into account BGP routes, which makes sense because the extended communities get added to the BGP routes. So let's just add these back in. And then I'll just show you the command, there we go. So that's essentially what we have as BGP configuration on the border leaf. So we've got the specific networks that belong to the VRF in there. You could, do a redistribute direct if you really wanted to, and then we've got the aggregate addresses. So we'll do that in DC2 as well. So DC2 leaf 1, we'll see that that should have actually gone back to how it was before now, where we see this route that's come over from DC1. So into BGP 200 tenant 1, .10.10.1.0/24, and then we'll do the same for tenant 2 like so. Let's do a show run section BGP just to again show the full end-to-end configuration. So pretty much the same as DC1, just with different addresses essentially. So let's just do a full connectivity test on here. So let's try everything layer 2. So 11, 12, 13, and then let's jump to layer 3. So 10, 11, 12, and 13. So we do have full connectivity across the whole fabric, even though now we've got the two VLANs in separate VRFs. And we can see, if we do a bit of a BGP verification on the leaves, let's do a show BGP L3VPN EVPN. Let's look at in fact, yeah, 10.20.1.13, so something from the opposite data center. We'll see there's a lot of stuff in here, and we'll see the L3VNI stuff here as well, so we can see that this is in the Tenant 2 VNI, because we can see 102 there. So these route targets are what essentially kind of tell where that traffic's coming from and where it's destined for. So we can see the L3 stuff here, we can see the L2 stuff here, and then this is essentially a combination of both of them. So we can see all that. I mean, it's a lot of information, but we can see that it's all being shared properly, and we can see that it's coming from the other data center, because we can see the multi-site loopback in there as well, which is all good. So that's it for now. We've configured all of the layer 3 connectivity we needed to allow the PCs to communicate with each other and for them to communicate between two separate VRFs. So in the next video we'll involve these firewalls, and we'll do a bit of route leaking from the firewalls to get the PCs outside of the fabric, because at the minute everything's just contained within the fabric. There's no access outside, and there's no access to the internet or anything. So hope to see you there.